Okay, so hello everyone. So welcome to this live problem solving session for the week 2 of the course Introduction to Galois Theory, instructed by Professor Krishna Hanumanthu. So I am Siddhartha Pramanik. I am a PhD student at IIT Kharagpur. Uh, Before start solving some problems, so first I will try to summarize the contents of the second week. So during the session, if you have any doubts, just feel free to ask. Okay. So in the first week, we basically have done the prerequisites, and in the second week, we will mainly start with the things that we are going to do. So in the first lecture, we have proved some uniqueness results. So the first is uniqueness of splitting fields. So that means if you have a polynomial, let's say fx over some ring f of x where f is a field, then its splitting field is unique up to isomorphism. So that is the thing. And the second one is we have proved the uniqueness of the algebraic closure. So these two things are important that we have done. And after that, we have seen some concrete examples uh, that how to find splitting fields of polynomials. So some examples of splitting fields. Okay, so we will see later that splitting fields are important because these are basically gives a characterization of normal extensions, and Galois extensions are particularly one kind of normal extension. So these three things is about the first lecture, and in the second lecture we have seen how algebraic elements behave under field homomorphisms. So let me write this: how algebraic elements behave under field homomorphism. So basically, if you have a field extension, if you have a field K, and suppose you have an extension K over F, and let's say you have an field homomorphism from K to K prime, let's say it's sigma, and suppose the image of F under sigma, it's F prime, so K prime over F prime is a field extension. So sigma is a field homomorphism from K to K prime, and image of F is just F prime. Now if you take an element alpha and say it is algebraic over F, then its image sigma alpha. So this will be algebraic over F prime. So that is the result. So algebraic elements maps to algebraic elements under field homomorphisms. This is also important to determine the uh, field homomorphisms, possible field homomorphisms. And next, we have seen that so over algebraic extensions, so if you take a field homomorphism of that extension, so it will be an isomorphism. So field homomorphisms are always injective, but if it is algebraic, it has to be an isomorphism. So field homomorphisms are field isomorphisms. So what this basically says is, so if you have an extension K over F, and suppose this is an algebraic extension, and if you take a just a homomorphism from K2 itself, F homomorphism, so it fixes F. So sigma is F homomorphism. Then sigma has to be an F automorphism. So this is the result. Next, we have defined prime subfields. So this is basically the smallest field contained in a field. So it depends on the characteristic. If characteristic is 0, then it has to be the field of rational numbers. And if the characteristic is p, a prime number, then it has to be the z mod pz. Then we have seen that field homomorphisms are always fixes the prime subfield. So field homomorphisms always fixes prime subfield. So that means if you take any field K, and if you take a field homomorphism, let's say sigma from K to L, then both has to be the same prime subfield. Because both has to be of same characteristic, and sigma of A must be A for all A belongs to A. So sigma has to fix the prime subfield. So this is the second lecture. Next, we move to the Galois theory, the main part of this course. So for that, we need some basic results about the group characters. So we have defined what do we mean by group characters. So these are basically a homomorphism, group homomorphism from a group to the multiplicative group of a field. So we have defined group characters. We have seen some examples. Then we have defined the notion of independent characters. So this thing is important, and we will use several times this concept. And we have proved the important result, the Dedekind lemma. So Dedekind lemma is basically that if you have distinct characters, then those distinct characters has to be independent. And we have seen some consequence that we are going to use mainly. So this is the third lecture. Then we come to the main thing, that fixed fields and Galois groups. So we have defined fixed fields. We have seen several examples, and after that we have done two theorems on fixed fields. So two theorems on fixed fields. So this is the beginning of the Galois theory. We will use these two results frequently. So first one is basically K over the fixed field of S has to be of cardinality S. So what is this? So S is basically a collection of field homomorphisms where sigma I from K to L, these are field homomorphisms. So a collection of finitely many homomorphisms. Then if you take the fixed field of this homomorphism sigma 1 up to sigma n, which is denoted by Ks, then this degree of this extension has to be at least cardinality of S. So Ks is the fixed field of S. So this is the first theorem on fixed field. And second one is K, degree of the extension K over Kg has to be equal to the cardinality of the group. So what is this? This basically, so K is a field, G is a group of automorphisms. So G is a group and cardinality of G is finite, right? So we are taking a field and taking a finite group of automorphisms. Then if you take the fixed field Kg and look at its degree of extension, then it has to be the degree of the group. So this is important. So these two theorems on fixed fields will be used repeatedly. So you need to understand these results. Then then we have defined the Galois group. So what is Galois group? We have defined. So Galois group is basically the reverse thing. Here we are taking field homomorphisms and looking at the fixed field. And here what we will do, so here we will take an extension K over F and look at the automorphisms of K which fixes the base field F. So sigma belongs to F such that sigma fixes F, where K over F is the field extension. Then we say sigma belongs to the Galois group of K over F. And we have seen some examples of these things, I hope. So I will do some more examples in this types. So these are the contents of the second week. Okay, so let's do some problems. So we have already seen some examples of splitting field. So let's do one more to to give a to get a good understanding of this thing. So this is problem number 1. Find the splitting field of the polynomial x power 4 plus x square plus 1, where the base field is q, the field of rational numbers. How to find the splitting field of this polynomial over q? So splitting field means the smallest field extension of q in which this polynomial splits completely, right? That means we can write this polynomial as product of linear factors. So we need to find the smallest extension in which this thing happens. So 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 for that, first the important thing is we need to find the roots of these polynomials. So how to find the roots of this polynomial? So first we need to find the roots of let's say f of x is x power 4 plus x square plus 1. So so let's see how to find the roots of this. So this is a degree 4 polynomial, so there are lengthier processes, but in this case we can do it easily. So observe that, so we can write this polynomial as x power 4 plus 2x square plus 1 minus x square, and this is basically x square plus 1 whole square minus x square. And if you write this, then it is x square plus x plus 1 times x square minus x plus 1. So so this is basically product of these two quadratic polynomials, and we know how to find the roots of quadratic polynomials. There is a straightforward formula, so let's apply that. So what are the roots of this part? So this is minus 1 plus minus b square minus 4 by 2, and the roots of this part is these roots are 1 plus minus 1 minus 4 by 2. So basically these are minus 1 plus minus root 3i by 2, and this is 1 plus minus root 3i by 2. So these are the roots. There are 4 roots, and this is a degree 4 polynomial. So if we attach these roots to the base field q, then what we will get? So now, so let's attach the roots. So minus 1 plus minus root 3i by 2 comma 1 plus minus root 3i by 2. So we need to write this field in the most simpler form. So how to write it? So this minus 1 and 2, these are elements of q itself. So it will absorb its own elements. So this is basically q adjoint plus minus root 3i. And since it's a field, so it is just q adjoint root 3i. So this is the smallest field which contains all the roots, and we know that so what will be the degree of this extension? So degree of this extension is also 2, that is also easy to find. So let me write this. So this is the splitting field. So it is the splitting field of F over Q, because you will not get a smaller field. Why you will not get smaller field? Because this degree is 2. Because in this field the polynomial F splits completely because it contains all the roots, and it is the smallest such field because root 3i has degree 2, as it satisfies the polynomials x square plus 3. You can check that thing easily. So this is about splitting fields. Now let's do something on the group characters. Okay, the second one. So let G be the group Z mod 2Z cross Z mod 4Z. Then find the number of characters of G in the field C, field of complex numbers. So we need to find how many characters of G are there in field C. So what do we mean by character? So phi is a character of G in C. That means phi is a group homomorphism from G to the multiplicative group of C. So this is basically C minus 0. So we need to find how many group homomorphisms are there. So let me write this. So we need to find the number of group homomorphisms from G to the multiplicative group of C, so which is C cross. So C cross is basically C minus 0, this group. So how to find this? So let phi from G, so okay, let me write the group itself. Z mod 2Z cross Z mod 4Z to C cross be a group homomorphism. Right? So we need to find how many possibilities of phi are there. So observe that Z mod 2Z and Z mod 4Z are abelian groups. So this Cartesian product is also abelian. So all its subgroups are normal. So now how to find this group homomorphism? So first thing we need to observe that what are the choices for this kernel of phi. Okay, so we need to look at the kernels. Why? Why we need to look at the kernels? So because if we use the first isomorphism theorem, so by first isomorphism theorem of groups, so this is our group G. So G mod car phi is isomorphic to phi of G. which is basically a subgroup of the C cross, right? So we need to find basically how many images of these things can lie in the C cross. So first of all, we need to find the possibilities of the kernel. So the possibilities of car phi are, so can you say which subgroups of G uh, can be the kernel of this homomorphism using the properties of group homomorphism? Yes, any answer? So first of all, kernels has to be a normal subgroup, right? But G is abelian, so every subgroup is normal. So we need some more restriction. How to?
18Z? 18Z?
Sorry.
No, 18Z, no, sorry.
So what are the first? What are the subgroups of this thing?
This is isomorphic to Z mode 18Z, right?
Z mod 18Z? No, no, it is 4Z.
Oh, I'm sorry, sorry, sorry.
Maybe
No,
my
okay.
writing is
Oh,
funky. Yeah. So we need to find the number of homomorphisms. So first let's look at the kernel. So let's write down the subgroups. So first of all, kernel can be the trivial subgroup. It can be the whole group. So I'm just listing down all the subgroups first. Then we will discard one by one. And it can be
so, yes, sir. Oh, the can go to 0 and 1 3 can go to 0.
so those are the only choices. Are you saying, or
Yes, sir. Only choices.
why?
These are generators.
Can you repeat the generators once more?
Uh, in Z mode 2Z, 1 is the only generator. In Z mode 4Z, 1 and I mean class of 1 and 3, 1 3 bar.
Yes.
So this so one class of 1 class of 1 goes to 0 and 1 3 goes to 0.
No, I want to see the possibilities of the kernel. What can be the kernel? So first, let me list down the all the subgroups. Then we will see which one can be the choice for the kernel. So it can be Z mod 2Z cross 0, or it can be 0 cross Z mod 4Z. It can be 0 cross the subgroup generated by 2. It can be Z mod 2Z cross the subgroup generated by 2. So I think these are the only subgroups. There are total 6. Yes. So these are the all 6 subgroups of this group G. Now let's see which one can be the kernel. So let me write in black. So these are all subgroups of G, which is Z mod 2Z cross Z mod 4Z. Now let's see one by one. So case 1, can the kernel be identity? So kernel means identity means phi is injective. So that means C cross contains a subgroup which is isomorphic to G. Is it possible? So can this C cross contains a group which is isomorphic to this Z mod 2Z cross Z mod 4Z?
Sir, no. It
Why?
has uh, C star is we have two elements. The C star is integral domain, right?
C star is not a field. C is a field, right? C star is a multiplicative group of C.
Okay, okay, I'm sorry. So,
Now see, this group, how many elements of order 2 are there? There are two elements, right? So this in this group G, there are two
yes,
elements of order 2.
one, 1, 2.
Yes, 1 comma 0 and sorry, three elements are there, 1 comma 2
2.
and 0 comma 2.
Sir, 1, 0 has order.
1 comma 0 has order
Order.
2, right?
Yes.
So these three
0.
elements are there of order 2. But in C star, there is only one element of order 2. Why? Because x square plus 1, this polynomial, how many solutions are there? Only two solutions. One is minus 1 and the plus 1. This is the only element. So definitely this cannot be a subgroup of C star. So which is a contradiction. So why this is contradiction? Because C cross has only one element of order 2, but G has three elements of order 2. So I hope this thing is clear. So kernel cannot be the identity, right? So this one option gone. So let's check the other one. So case 2, kernel is the whole group G. So if kernel is the whole group G, so that will imply phi is the trivial homomorphism. And this is possible, right? So trivial homomorphism is always a homomorphism. So in this case, we have one homomorphism. So this is possible. Now let's check this third case. So case 3, where the kernel of phi is basically Z mod 2Z cross 0. Now, is it possible? Can this subgroup is kernel? So if this is the kernel, then what about Gmod car phi? Then Gmod car phi is basically Zmod 2Z cross Zmod 4Z modulo Zmod 2Z cross 0, and this is basically Zmod 4Z. So in this case, Zmod 4Z is isomorphic to a subgroup of C star, right? And this is possible, right? Because C star contains a cyclic group of order 4. So this is possible. But now how many such, so in this case, how many homomorphisms we will get? So now can you count the number of injective homomorphisms uh, from this to C cross? Yes.
If one goes to
Hello.
there are two possibilities for unit element. Either it
So
goes to the primitive root.
yeah, so basically we need to, so C cross has contains a subgroup which is isomorphic to Z mod 4Z. So we need to basically count the number of automorphisms of Z mod 4Z, because C cross has only one subgroup which is isomorphic to Z mod 4Z. So since C cross has only one subgroup uh, which is isomorphic to Z mod 4Z. So in this case, number of pi is uh, the cardinality of automorphisms of Z mod 4Z. Yeah, are you getting or do you have doubt? And this is basically 2. So in this case, we are getting 2 homomorphisms. And in the previous case, we have got 1 homomorphism. And in the case 1, we have no homomorphism. So here this is possible. So here we have 1 homomorphism, and in this case we have 2. Okay, so let me, so there are 4, sorry, yeah, 3 other choices. So I will do one more, and the rest cases are also similar. So let's just do one more case. So if you have any doubt, just unmute or write it in the chat box. Okay. Otherwise, I will not get that if you are understanding or not. So case 4. So in this case, kernel is basically uh, this one, 0 cross Z mod 4Z. So that will imply your G mod kernel phi is basically Z mod 2Z cross Z mod 4Z modulo 0 cross Z mod 4Z. So this is basically Z mod 2Z. So now we need to find uh, how many homomorphisms are injective homomorphisms are there from Z mod to Z to C.
Only one.
Only one, yes, correct. So in this case, there exists only one homomorphism. So this is the case 4. So this is also possible and we will get 1. And in these other two cases, so I will just write down and I will let you to check on your own. But if you are not able to do, you just let me know in the next class, I will do. Or maybe you can write it in the discussion forum also. Okay. So, so in this case, we will not get any homomorphism. And in this case, we will get homomorphism. Uh, and that is only one. So if we count, then total 1, 2, there are 5 homomorphisms. So you just do the case 5 and case 6. So these are exercise for you. So here you will get 0 and here 1. So there are total. So how many? Just 1, 2. There are 5 homomorphisms. So I hope this is okay. So these are the number of characters of this group to C. So the answer is 5. Okay. Now let's move on. So problem number 3. So we have defined we have defined fixed fields and we have also defined Galois groups. So let's see one important property that we have used repeatedly but we have not mentioned specifically or separately. I would like to mention it here. So let K be a field. Okay, let K be a field. Then show that. So we need to prove two things. First one is if you take two intermediate fields or sorry subfields, let's say f1 contained in f2 contained in k are two subfields, then what are the relation between their fixed fields? So then you have the Galois groups. So here we have k, here we have f2, here we have f1. So we can consider the Galois groups of this extension. So then you can consider the Galois group of k over f1 and you can consider the Galois group of k over f2. Then what will be the relation between these two? This is the first thing. And second thing is, if you take two groups, let's say G1 subset of G2 subset of automorphisms of K, B2 groups, B2 groups, then what will be the relation between their fixed fields? So you can consider the fixed field of the group G1, and also you can consider the fixed field of G2. Then what will be the relation between these two? Actually, we don't need groups. Set is enough. So let's write it in the more general form. B2 sets. Let's say S1 subset of S2 B2 sets. Then what are the relation between their fixed fields? So we have used these two things many times, but let's mention it specifically. So can you say what will be this first thing? So these two things are very easy, just observations. Yes, anyone? So let's see the first one.
So the first is contains the second.
Yes, sorry.
First is Galois K with six F1
Actually,
superset
your
of.
voice is very low. So can you speak more loudly?
Hello.
Yes.
So, sir, the first group Galois, uh, which fixes F1, is a superset of Galois, which fixes F2.
Yes, you are right. So this inclusion will be reversed, and it will be in the both case. Inclusion will be reversed in the both case. So let's write down this, and this is very easy to see. So why? So if sigma belongs to this Galois group of K over F2, that means sigma fixes F2, right? So sigma of A is equals to A for all A belongs to F2. But F1 is a subset of F2. So sigma also fixes F1 because F1 is a subset of F2. So that means sigma is in the Galois group of K over F1. So this proves the first part. And the second part is also same. So let's write down this. So let's take an element from the fixed field of S2. Then uh, sigma alpha of A is sigma beta of A for all sigma alpha, sigma beta in S2. So all homomorphisms fixes this element in S2. So that means sigma of alpha of A is sigma beta of A for all sigma alpha, sigma beta belongs to S1 also because S1 is subset of S2. So this means this A has to be in KS1. So this proves the second part. So just remember this thing that we always have this inclusion get reversed. So it will be
So,
helpful.
this group contains the other group, the later one.
Hmm.
So, the Galois group which fixes F2 is a subgroup of Galois group which fixes F1.
Yes.
So, is it normal, sir? Means need not be normal, right?
No, no, it need not be normal. There are conditions you will see later in the course, if and only conditions when it is normal. Okay, so try to remember these two things. These are important. Now let's see some examples of fixed fields and how to find those things. So in this course we will mostly see finite extensions, but here I want to mention some other things. So problem number 4. So define sigma from C to C by just conjugation. Sigma of Z goes to its conjugate Z bar, right? And let G be the group generated by this. So first thing is prove that sigma is an automorphism of C. So this thing is very easy. It's just a routine check. Second thing, if you take the group generated by this, then find the fixed field. So there are two things we need to do. So it's an automorphism of C, that is actually a routine check. So I just write trivial. But how to do the part B? How to find its fixed field? So any guess what will be the fixed field of this thing? Of this conjugation map or conjugation automorphism?
Actual axis, the real numbers.
Yeah, the real number. So there are two ways of doing this thing. So first, let me give the first method. First method you just compute directly. So let a plus ib, this complex number, is in the fixed field. So that will imply sigma of a plus ib is the same element. But what is this element? This element is basically the conjugate, right? So this is a minus ib is equals to a plus ib. So these two things has to be equal. But when this thing equals, so if you compare the real and imaginary part, then this so a and k gets cancelled. So 2 times ib is equals to 0. That means b has to be 0. So that means a has to be in R. And conversely, if a belongs to R, then definitely sigma fixes A, right? Because its conjugation itself, it has no imaginary part. So the fixed field is R. So this is the just simple checking. But second thing is to use the results. So our G is generated by sigma. So what is the order of this group? So then order of G is 2, because sigma square is the identity map on C. So if you take conjugate 2 times, you get the same element. So that means uh, if you take, if you know this degree, this is the cardinality of the group. This is 2. So this is the second theorem on fixed fields, right? And CG contains R. That is also easy to check. So from that we can conclude that CG is equal to R, because C is here, CG is here, and R is here. So this is 2 and this is also 2. So this has to be 1. Okay, so I hope so. This thing is easy, but these are just observations. So the fixed field is just the field of real numbers. Okay, let's move on. Problem number 5. So here let's find the Galois group of R over Q. So set of all automorphisms of R which fixes Q. So note that Q is the prime subfield, right? So this thing is basically the automorphisms of R, field automorphisms of R, because every field of automorphism fixes the prime subfield. So just let's find this thing. So let sigma belongs to this Galois group. Then what can we say about this field automorphism? My claim is sigma has to be identity on R. That means the Galois group has cardinality 1. It is just identity map on R. So this is my claim. So I will prove this in several steps. So first I will prove uh, if x is 0, then phi of sigma of x is also positive. If x is a positive real number, then its image is also a positive real number. So here I will use some results from the analysis. So since x is positive, there exists a real number y such that y square is equals to x. Okay, so this will imply sigma of x is basically sigma of y square, but sigma is a field automorphism. So it is sigma of y and square of this thing. And this has to be positive, right? Because x is non-zero, this will imply sigma of x is also non-zero. So field automorphisms are always, so its automorphism in particular it is injective. So sigma of x is positive. So we are using this result from analysis. You can go to any real analysis book. So sigma maps positive real numbers to positive real numbers. This is the first thing. Second, sigma is increasing. So how to prove this? So that means x greater than y will imply sigma of x is greater than sigma of y. So this thing we have to prove. But this is easy. So let x greater than y. So it will imply x minus y is positive. So its image will also be positive. Sigma of x minus y is positive. But what is this thing? This is sigma of x minus sigma of y. This is positive. So this will imply sigma of x is greater than sigma of y. So we are using the properties of field homomorphism. So sigma is increasing. Now the final step, sigma is identity. So we already know sigma fixes the rational numbers, right? So we need to prove that sigma fixes irrational numbers too. So how to prove this? So we will use contradiction. Suppose sigma is not the identity map, then there exists some real number such that sigma of x is not equals to x, right? Since sigma of x and x, these two real numbers are not equal, so that will imply either sigma x is less than x or sigma x is greater than x, right? But uh, if sigma x is less than x, so we know that rational numbers are dense in the real numbers. So let's use that fact. So this implies there exists a rational number q such that sigma x less than r less than x. Okay, so let me write down that. So we know q is dense in r, right? So that means between any two real number, we will find a rational number. So this is also a result from the analysis. So we are using that here. So sigma x and x, these are two distinct real numbers. So between any two distinct real numbers, we need to write that. Need to any two distinct real numbers, we will find a rational number. So we'll find a rational number r. So then uh, note that sigma x less than r. So but r is less than x. So r is less than x, but sigma is increasing. So sigma r is less than sigma x. But r is a rational number, so it has to be r. So here we are getting r is less than sigma x, and here we are getting sigma x is less than r. So this is a contradiction. Okay, so this is not possible. Sigma x cannot be less than x. On the other hand, if x less than sigma x, then similarly we will find another rational number between these two. So x less than s less than sigma x. So again we will use the same trick. X is less than s and sigma is increasing. So sigma x is less than sigma s, but s is rational number, so it has to be s. So here we are getting sigma x is less than s, and here s less than sigma x. So this is a contradiction. So in both cases we are getting contradiction. So this cannot happen. So what is wrong? So we have assumed that sigma is not equals to identity. So this is wrong. So hence sigma has to be the identity map. This completes this proof. So, is it okay? So I hope you got this. So next, problem number 6. Okay, so this is the automorphism of R over Q. Okay, let's do one more automorphism problem. So here, this is problem number 6. Okay, so let K be a field and let T, okay, let X and X be a variable over K, and let L be the field of all rational functions. So L be the field of rational functions. Okay, I hope you have seen this definition in the lectures. So then find, okay, not find, let's prove this. Then show that if sigma belongs to the Galois group of L over K, then sigma of T has to be some AT plus B by CT plus D, where A and C are non-zero. So these are the only automorphisms. Sorry, not E, it has to be X. My bad. AX plus B modulo CX plus D. So every automorphism of the rational field which fixes K has to be of this form. So these are called linear fractional transformations. So these are called, and this so in particular, so this will prove that the Galois group of this rational function field is basically uh, this this of this form. Okay, how to write this? So let's write this A B C D such that A B C D belongs to K and AC is non-zero. So I will write where sigma of A B C D of X is basically Ax plus B by Cx plus D. So, okay, so you understood this problem. So this is the set of all automorphism of Kx which fixes K. So we have to prove this. So to prove this, I need a result. So I will mention that. So how to prove this? So let sigma from kx to kx be an k automorphism, means this automorphism fixes k. Now what will be the image of x under this automorphism? So that has to be some rational function. So suppose image of x under sigma is the element uh, some p of x by q of x, right? Where px and qx are polynomials, and they're relatively coprime. So we are cancelling out all the common factors, and obviously qx has to be non-zero, otherwise it will be undefined. So this is the we are letting this is the image of x, but sigma is an automorphism, right? So since sigma is a k automorphism, so what will be the image of sigma? It has to be whole k of x, but in so k of x is generated by this single element x, right? So okay, let me write this. So k of x is equals to the whole image because it is surjective, but it has to be generated by the image of x because it fixes k. So it is k of px modulo qx. So why this is? So this equality because sigma is onto. And why this equality? Because kx is generated by k and x. So sigma of kx is generated by k and sigma of x because sigma fixes k. So is it okay? Are you following? Okay, I hope are so good. Now from this what can we say? So these two things are equal, right? So that means, so one thing you can observe that if you take kx here, then k of px by qx is a subfield of this, and k is the base field. So we have this tower, but we have equality here. So this degree has to be 1. So this means,
So when we say the when we say kx is generated by k and x, so we say as in like kx is an as an a algebra k algebra,
no, as a so
or
it is the smallest field containing a and x. Okay.
containing k and x. Okay, sir.
So x is a variable, right? So if you take the polynomial ring, So this is the smallest ring containing k and x. But if you want a field, so you need to go to the rational function field. So this degree k of px by qx, uh, this has to be 1 because they are equal. But there is a particular formula of this thing. So there is a result. So let me mention that. So this is this thing is basically maximum of degree of px comma degree of qx. So this part is exercise for you. So this is not difficult. So I will use this. If you are not able to do, then just let me know in the next tutorial class maybe. So this means this maximum of degree of px comma degree of qx is 1. So both degree px and degree qx are 1. Right? So these are degree 1 polynomials. So that's here the proof ends. So this means px has to be some ax plus b, where ab belongs to k and a is non-zero because this degree is 1, and qx is also some cx plus d, where c comma d belongs to k and c is non-zero. And okay, we have also one more condition, I think. Okay, so there is one more condition. So here AD minus BC has to be non-zero, and AD minus BC has to be non-zero. So what will happen if AD minus BC is 0? And also note that, so okay, so first let me write down this. So we already got, so this will imply sigma of x, which we have assumed px by qx. So it is just ax plus b by cx plus d. So this form we have got. Now find the final condition. So also note that AD minus BC is non-zero. Why? So what will happen if this is 0? Because if AD minus BC is 0, so then these two things are scalar multiple of each other, right? So these things will cancel. So this will imply uh, A by B is equals to C by D. So these things will cancel out and you will get a constant. So basically ax plus b by cx plus d will some constant, let's say d prime belongs to k. But that is not possible, right? So this is contradiction. And why it is a contradiction? Because the fixed field is k. So we cannot get other elements in the k, because sigma of k has to be k, right? and sigma is bijection. So this will imply sigma of x equals to d prime belongs to k. This is a contradiction. So is it okay? So this completes the proof. So here we have got the all Galois group of the rational function field over the base field k. So this is the description. So I have to leave one thing for you to check. So this you can do. So let's do some other problems. Okay, let's do some problems on the Galois group. So let's do one concrete example. So determine,
Uh, in general, I wanted to ask, sir,
yeah,
some. I also joined one course on algebraic geometry and commutative algebra.
okay.
His timing session is same as this Galois problem solving session. So
Uh,
I'm finding
that
little
I
difficult
don't
because
know
it's all
actually
to
because that
join
is
that.
a independent thing, right? So I am not aware of that thing.
So because I have some doubts in that, so I need to join that part as well. So
Yeah, that is up to you. Okay, so that is independent course, so I cannot interfere that thing.
means timings cannot be like rescheduled like this
No,
like
actually,
or
this we have fixed independently. I am not aware of those courses, so we fix these timings according to our free time. Okay.
okay, sir.
So if you have doubts, you can also put in the discussion forum. There is a discussion forum. You can write there also.
Okay, sir. Thank you.
Yeah. Okay. So determine the Galois group. Uh, Galois group of Q adjoint fourth root of 2 over Q root of 2. Okay, so how to find the Galois group? Galois group means automorphisms of this which fixes this base field Q root 2. So let's draw this picture. So here we have Q adjoint real fourth root of 2, and here we have Q adjoint root 2, and here we have the prime subfield which is Q. So we know how to find, so we have seen how to find the Galois group of this. So we need to find Galois group of this thing. So the first thing is, so let sigma from Q adjoint fourth root of 2 to Q adjoint fourth of root of 2 be a Q root 2 automorphism. Right. So then sigma is completely determined by the image of by sigma of this thing, right? Because this thing generates the whole field. So only we need to check the image of the generator. So what are the possibilities of this image? We need to find that thing. So we need to find the number of, okay, we need to explicitly find, we need to find the possible images of this under sigma in q fourth root 2. So how to find this? So we know that we have already mentioned in the beginning that how algebraic elements behave under homomorphism, right? That we have mentioned how algebraic elements behave under field homomorphism. So uh, they have to, their image is also algebraic, and this has to be the root of the same irreducible polynomial. So first thing, let's determine the irreducible polynomial of 4 root 2 in q root 2. So I will just write it down. First thing is x square minus q root 2. This is the irreducible polynomial of real fourth root 2 over q root 2. So you just check this. I am just writing the facts. These are easy to do. The second thing is, what are the roots? Roots of x square minus root 2 are the real fourth root of 2 and the negative of this. These are belongs to q adjoint this. So we have only two roots. That means we have only two choices. So the Galois group of this now is easy to find. So this is basically 1 comma sigma. Where what is sigma? Where sigma maps this thing to its negative, and the other one is identity, so it fixes the same element. So we have only two elements in the Galois group. So this is the description of the Galois group. Okay, let's do maybe one more problem, maybe easier one. Okay, so let k over f be a field extension. Okay, and sigma from k to k prime be a field homomorphism. So this is a field extension, this is a field homomorphism. So let me draw the picture here. Here you have k and here you have k prime. This is the map sigma. And here you have the extension f. And let me assume, okay, so suppose uh, f prime is the image of f under sigma. So this is sigma of f, which is f prime. So here we also can restrict sigma. Then show that the Galois group of k over f is isomorphic to Galois group of K prime over F prime. So these two Galois groups will be isomorphic. Okay, so I hope you have understood the question. Sorry, we need to field isomorphism. Otherwise, it will not be true. So this is an isomorphism. Then the Galois group will be isomorphic. So how to prove this? So defined. So we need to prove that these two groups are isomorphic. That means we need to produce an isomorphism. So let's do that. So define, so using this sigma, we will define a group homomorphism. So let's call it sigma bar. So this is from Galois group of K over F to the Galois group of K prime over F prime. And how it is defined? So just sigma bar of some, let's say phi. So this will be, so let's see how to do this. So, so here you have a map from K to K. This is phi, and from K to K prime we have sigma, and we want to create a map from K prime to K prime. So what we can do, we can take here K prime and take sigma inverse. So what is this? Am I doing right or? So this is sigma phi sigma inverse, right? So we are defining this. So we need to check several things. So what we need to check? The first thing is sigma bar is well defined. So why it is well defined? We need to check that its image is lying in this set. So since sigma phi are automorphisms, so they are automorphisms. So sigma phi sigma inverse is also an automorphism. So these are just trivial things, so that, so I am just writing the main points. And clearly sigma phi sigma inverse belongs to the Galois group of K prime over F prime, because we are getting this composition. So it is well defined. Okay, now we need to check it is a group isomorphism. So checking bijection and group homomorphism, those are trivial things. So, but let me write it down for your convenience. So it is a group homomorphism. So how to prove that it is a group homomorphism? So sigma bar of phi 1 and phi 2, by definition it is sigma phi 1 phi 2 sigma inverse, right? Now we can write this as sigma phi 1 sigma inverse sigma phi 2 sigma inverse. Now let's take this brackets. So this first part is basically sigma bar of phi 1. and the second bracket is sigma bar of phi 2. So it is a group homomorphism, it's clear. Now the injectiveness. So why it is injective? So sigma bar of phi 1 equals to sigma bar of phi 2. So it will imply sigma phi 1 sigma inverse equals to sigma phi 2 sigma inverse. So let's multiply with sigma inverse from the left and sigma from the right. Sigma inverse sigma phi 1 sigma inverse sigma inverse sigma phi 2 sigma inverse sigma. So that will imply phi 1 equals to phi 2. So it is injective. And the surjectiveness is also easy. So let phi prime belongs to the Galois group of the right hand side, k prime comma f prime. Right. So we need to produce. So we are taking an element here. We need to produce a p-image here. So you just check that sigma inverse phi prime sigma belongs to the Galois group of k over f, and sigma bar of this element is sigma inverse phi prime sigma inverse, which is basically phi prime. So this is the p-image. So this is onto. Hence the Galois group is isomorphic. So this completes the proof. So this is just a routine check. So once you have defined this map, then everything is follows immediately. There is nothing difficult. It's just straightforward. So I think this is enough for the second week. So can you provide these contents? So are you talking about these notes?
Yes, sir.
So it is in that folder, right? So you have the
Mm.
access to that Google Sheet. There you
Okay.
can see the link for the folder where you will get all the notes.
Okay.
Yeah. So do you have any other doubt? So if you have no doubts, then maybe we can stop. Let me stop the recording first.
So,
Yeah, tell me.
one doubt. How to find algebraic closure of Q, basically.
So it is the set of all algebraic numbers. So I don't know if
Mm.
there is any specific description of that, but
Mm.
it is a proper subfield of C and contains R, but no, it does not contain R. There are real numbers which are not algebraic. Yeah, I don't think there is any specific description of this thing.
So, mainly, what is the procedure behind it? Ki if we take one polynomial and include roots.
Yeah, the Artin's construction. Yeah, basically you adjoin the roots of all the reducible polynomials, then you see the extension.
Okay. Thank you, sir.
Yeah, yeah. Any other doubts or queries?
Yes.
Yeah.